moving on. If you want to be more technical, especially for engineers, and focusing on the power and control aspect of our robotic system, this is our basic architecture. Okay, so as you can see, we have the perception components, our sensors, and we collect them. They are fed, they are delivered to our controller or anything that has a CPU. Okay, controller, microprocessor, microcomputer. Okay, and then sorry, whatever is the process data, the CPU will forward that to the pre-programmed instructions. It will be inputted to those pre-programmed instructions, and the corresponding output for the pre-programmed instructions, meaning for each input, there's a corresponding output. Okay, and that output will be converted into mechanical action. Okay, but at the same time, the CPU also allows the user um, to provide additional instructions like sudden um, sudden stopping. For example, if you want the robot to stop immediately because of some reasons, then that could be an additional instruction, right? In Big Hero 6, again, uh, Baymax is able to accept additional instructions from time to time. Okay, and that's actually the concept of machine learning. Okay, it's updating its pre-programmed instructions based on the additional instructions. So it updates its machine learning model. If you have, again, if you have seen in the movie, Baymax learned a lot from Hero and from the things that Hero wanted him to learn. Okay, like karate and flying. So that's actually an example of machine learning. And the additional instructions can either be directly converted into mechanical actions, or maybe they are just meant to update our pre-programmed instructions, especially when learning or adapting. But in normal cases, this happens both. Okay, it for emergency actions, they are being executed immediately, wh while at the same time, the those additional instructions are updating the pre-programmed instructions. Okay, so that's regarding the control part of our robotic system. Now, regarding the architecture of the physical structure of a robot, okay, physical, structural, and mechanical aspect of the robot, then it depends. If it is a manipulator robot, then it must have these portions or components of its manipulator. Okay, the manipulator basically has, of course, the base where it is attached to. Um, it must have the links, different links, okay, depending on your application. The more links, the more complicated that robot is. Or in other words, the more complicated the task of the robot, the more links it requires. Okay, so the links actually join the two adjacent joints of a robot. So the joints basically they are motors, okay, that allow the turning of the links, right? So again, when it comes to the hand of the manipulator, they could be vacuum grippers, magnetic grippers, or some general purpose end effectors. All right. So that's for the basic architecture. We have the control part and we have the physical part. Our focus is more on the control part. Okay, since we are electronics engineers in the making, right? So now another thing, although this is more on the physical part, but this is where we uh where the two aspects converge. Okay, we have the control part and we have the physical part, and they are both of them are directly involved in what we call robot motion and configuration. Okay, so um, basically this is how our robots move, right? Especially within the context of manipulation robots. So we have the Cartesian coordinate configuration. So when we say Cartesian or rectangular, it moves only in linear paths or linear directions, up, down, forward, backward, forward, backward, left or right. Okay, so that's Cartesian. But if you want it to move like spiral thing, a spiral movement, then that's the cylindrical. Okay, it can move around. At the same time, it can adjust its end, the height of its end effector. Okay, it can operate at this level, at this level, at this level, and it can go around. So that's cylindrical. And we also have the spherical and the articulated. So for you to appreciate it more, let's watch this video. Okay, it has no audio. I will no, right. So Cartesian robot, we have here, like what I said, it moves in a linear motion. Okay, left or right, front to back, and vice versa, or up and down. Right? So rectilinear or prismatic robots or Cartesian robots, okay, they move according to the Cartesian coordinate system. Okay, we have the cylindrical, like what I said. Okay, it can move around, and at the same time, it can adjust the height where it is moving. Okay, so that's cylindrical motion or configuration. We have the polar, which is okay, I think this is the most common um for beginners, most common type of robotic arm or manipulation robot for beginners. And we also have the Scara. Okay, this is just like a polar robot, a more advanced one. Okay, as you can see, it has multiple joints. Selectively compliant arm for robotic assembly, Scara. Okay, we also have the jointed arm. Still, this is a polar robot with additional points, but the movement is different. Okay, so observe the movement. And I think this is the more advanced, common type of robotic arms that are recommended for beginners. Okay, so I think that would be all. On the right side, as you can see, it's very important when we are designing to be aware of these aspects or these concepts. Okay, we have the human work envelope. If there's a human involved in the operation of the robot, then you have to consider the space of the robot's motion and configuration. Okay, of course, first law of robotics, the robot must not harm the human being. Okay, so that's why when we design, we make sure the human operator has enough human work envelope. Okay, to for him to work safely with the robot. Right? We also have the shared workspace. This is where the robot and the human being interact together physically. Okay. You have the robot work envelope and the feeding system. So these are additional spaces that the robot may occupy whenever it moves. Okay. So we have to consider this, and this is especially for the safety aspect of our design. Okay. And we have the context of mechatronics. So Um, you may have seen already that robotics and mechatronics are somewhat being interchanged, or they always appear together. Okay, if we mention robotics, then there will always be mechatronics, or vice versa, because actually robotics applies the concept of or the discipline of mechatronics. Okay, so this is more like the combination of the different fields. of um, fields that are involved in electronic systems, control systems, computers, and mechanical systems. Okay. Um, just like robots, there are many other machines that have similar architecture. Okay. So, okay, just like robots, a mechatronic system usually has, uh, not usually, should have a mechanical system. Okay. And that mechanical system already includes the actuators and sensors, right? That's for the mechanical part. For the electronic system and control system, we have the input signal conditioning and interfacing, which is composed of circuits, different circuits like amplifiers and filters. Okay, and since we are normally using computers or digital controllers, these signals must be converted into digital form. Okay, so that they can be processed here and at the same time so that they can accept input or provide output via the user interface. Okay. And at the same time, if we have the input signal conditioning, we also have the output signal conditioning, and the output of that will be fed to the actuators. Okay. So mechatronics, you can observe the different mechatronics products, and you can actually apply them in your robotics design. Okay, and but most importantly, we must understand how a machine works. Okay, we go back to most um the most basic essence of a machine, okay, which is actually any device that transmits or modifies energy to do a job better and faster and more powerfully than a human being does. Okay. Machine. What is a machine? If you can still remember, if you have watched already, Three Idiots, okay, there's a scene where Rancho has to argue with this professor regarding the definition of a machine. And Rancho's definition is somewhat like this, actually. Right? I'd like to highlight the word job better. Okay? The machines are meant to help us do our job better. Okay? Better in a sense that it requires less effort from us, less energy, less time, but producing better results, more accurate results, faster results, more intense performance. Okay? Um, and in physics, machines are classified as, or especially simple machines, can be either an inclined plane, as simple as an inclined plane, a pulley, a lever, a wedge, a wheel and axle, and a screw. So I'm not going to discuss this one by one, but I just want you to observe. Um, some robots like conveyors have an inclined plane. Okay, and what I want you to realize is that we basically use the same principles in like what we have learned in physics, okay, regarding inclined planes. All right, so we just apply them. Same thing with the pulleys. Okay, we have some conversion factors here, right? Depending on the size of the wheels or this circular thing, okay, or the length of the strings, right? And one possible or one common application for that is the robotic component of our cranes and other heavy machines in construction. Okay. Lever. Okay, we usually use the levers in anything that has um, hinges or something being screwed. Um, Scissor could be a simple example for that. In the context of robotics, of course, the grippers. The grippers are example of a lever machine. Okay. So while next we have the screw, of course, screws are meant to be fastening one form to another. And at the same time, screws are actually the pattern of our cylindrical robots. Okay? So remember, the more you rotate this one, the more it goes down or maybe goes up. Okay? So the motion of the screw is actually cylindrical, right? And we can apply that also in our robotics system. Okay, of course, wheel and axle, especially for mobile robots. Whenever we have motors, there will be wheels and axles. Okay, and the wedge, we can apply this also especially in the physical construction of our robotic system. Okay, so this is for the mechanical aspect, and this is just an overview. We're not going to dig deep on these concepts, but it will be nice. It will be better if you know these things, right? But not our priority, because our priority will be in our last discussion or in last section of this module, right? So before we go to that part, take note that a machine has structural components. Okay, structural could be a frame member, uh, axles, bearings, seals, splines, fasteners, whatever hold things together, whatever forms the body of your robot. Okay, and of course, we also have the common mechanism components of a robot. These are if the common structural components are meant to put our different components together or in place. These components are meant to move some components like the arm, the legs, the wheels, so mechanism. And that includes the gear trains, the belt drives, chain drives, linkages, brakes, clutches, the common follower systems. Okay, so you can check this if you want to explore the mechanical aspect of robotic systems. But unfortunately, this course that we have more focuses on the electronic side. Okay, so lastly, this is where we focus on common control components of a machine. So we have the system, the controller system, and then we have the sensors, different sensors, and different actuators. Okay, so we can have a pressure sensor, sonar, ultrasonic, piezoelectric microphones, and so on. Okay, we can also, regarding the monitoring of the movement of the robot, we have the gyro sensors and the MEMS or micro electromechanical system. Okay, this is yeah, it's just a very small microchip embedded in our robotic systems and even in our phones because they allow the system to measure the orientation or the movement of the robot or of the body of the system. Okay, so regarding the actuators, again, we have the motors. We can also have relays and valves for turning on, turning off, or opening and closing something. What else? We can have pneumatic and hydraulic actuators as well, right? So, in summary, we have the input device, at least one input device. Then that could be a sensor, a switcher, or some adjusters, like our switches and sliders or knobs. While on the output side, we should have at least one actuator or indicator. Actuator, of course, the motor's indicator, we can have some screen or as simple as LEDs. Okay? So this is where we focus on as easy is, right? And we're going to have an overview of that in the next section.